Great. So our own Clement will tell us that there is a completely separable mat family of vector spaces.
Okay, so thanks for being here. Well, mat families or subsets of omega, of course, has been studied for quite a while. But mat families of vector spaces is something that only started about a decade ago, approximately, slightly less than that. So there's still a bunch of open problems regarding whether the existence of certain mat families of subspaces satisfying certain properties. And today I'll be talking about completely separable mat families. So let's start with some basic definitions and setup. We'll be focusing on a countable vector space, and more precisely, a space over a countable, possibly finite field with countable infinite dimension. And for this whole talk, I'm going to fix a basis, Helmholtz basis, of course, of ENs, okay? So in the context of vector space, almost disjoint for two subspaces, infinite dimensional subspaces, they are almost disjoint if their intersection is finite dimensional, okay? And one quick important remark is that I'm going to be ignoring the zero vector for this whole talk. So for example, when I say that two subspaces are disjoint, what I really meant is that that intersection is trivial, okay? So with a notion of almost disjoint, then we can define a notion of almost disjoint family, which gives us a notion of mat families. It's the same thing, nothing new. And which allows us to define a cardinal, right? Because when we have this kind of families, the natural question is to ask what's the smallest possible cardinality. So AVEC, I will define it as the smallest possible cardinality. I should include infinite. There's a mat family of size 1, of course, which is the whole E. So the minimum size of an infinite mat family of block subspaces, I'll get to what block subspace in a moment, okay? And it does turn out that this is a cardinal invariant. This is uncountable. So this was proved by Ian Smythe in 2019. So it is meaningful to talk about AVEC, therefore. Okay, block subspaces. Like I mentioned, we fixed a Helmholtz basis of ENs. So each vector can be written as a finite linear combination of ENs. So I define the support as the set of n's, the indices, with non-zero coefficients. Okay? And this allows us to,
Question, is the whole space the only finite mat family?
Yes, so that's non-trivial, but yes. This is yes, yeah. Okay, yeah, so this support, this allows us to define a partial on the set of vectors. So if the support of X lies entirely below the support of Y, then we simply just say that X is less than Y, okay? And this partial order allows us to define a notion of block sequence, which allows us to form a notion of block subspace. So a block sequence, sorry? Oh, this? Oh, okay. Okay. So a block sequence is basically a sequence of increasing vectors with respect to the partial order that I just mentioned. Okay. And so a block subspace is a subspace which has a block sequence as a basis. Okay. I mean, the block sequence is linearly independent, right? Because they are disjoint, they have disjoint supports. Block bases are unique up to scalar multiplication. So what that means is that we can just kind of conflate between the two. So what I mean by conflate is that I can just treat block subspaces as block sequences, and sometimes I will treat block sequences as block subspaces. There isn't much generality loss between the two. There's a very good reason why I brought up block subspaces. The first reason is because I guess the first reason is because they are just a lot easier to deal with than arbitrary subspace. And the second reason is because it turns out that every infinite dimensional subspace contains an infinite dimensional block subspace. So what this means is that when we are dealing with block subspaces, we are dealing with a dense collection of subspace. Okay, so to a certain extent, not all generality is lost. For example, if you want to check whether an almost disjoint family is maximal, we just need to check it with respect to block subspaces. Okay, so this is block subspaces. Just a couple of notation. I'm going to use E infinity to denote the set of block sequences, which are block subspaces, of course. Oh, just one more thing. For this talk, when I use the word subspace, by default, I'm referring to infinite dimensional, unless stated otherwise, okay? And I'm going to use the angle bracket to denote span. Okay, so these are vector spaces stuff. But let's just go back to a moment. Let's go back to almost disjoint families of subsets of omega again, because we will be using some of these for our discussion on vector spaces later. So if A is an almost disjoint family on omega, then we can define this ideal, I of A, which is basically the ideal generated by finite unions of elements of this almost disjoint family. Of course, it's not too hard to check that this is indeed an ideal. This gives us a couple more things. So I plus A is just the set of things that are not in the ideal. And I double plus A is a set of sets which are compatible with infinitely many elements of A. So by compatible in this case, I just mean infinite intersection, of course. And the reason why, or one reason why there's this, we introduce I plus plus A is because in the scenario where A is maximal, these two collections of sets coincide. Okay? Okay, so, and this gives us the definition of completely separable mat family. So if A is almost disjoint family, and such that every positive set contains an element of this almost disjoint family, then this is completely separable. Okay? It's not too hard to check that every completely separable almost disjoint family is maximal. It turns out that completely separable map families is a very powerful set theoretic object, and it has applications in multiple places. And it was first introduced approximately 30 plus to 40 years ago. Sorry, is this wrong? Oh, it's much older than that. Oh, I thought that was the first paper, actually. Oh, I see, I see. Okay, so it's much older than that, it turns out. But what Belker and Clement showed was that under this assumption, there is a completely separable map family. And so ever since then, there have been various efforts in trying to weaken the set theoretic hypothesis. A few.
Mention the question of Erdős from 72 first.
Okay,
Does there exist one of these things?
I see.
This is not the first place it was introduced, but
Okay.
they asked this question in 1972.
Okay,
It's still open.
okay, yes. Yeah, okay. So going back to the efforts on trying to answer the question that Dilip just mentioned, is whether there is one in ZFC. So Shea came pretty close in 2011 when he showed that either if S is strictly less than an A, or the other way around, but assuming a certain very weak PCF hypothesis, okay, which, for example, if the continuum less than lambda omega, then this holds.
So there are three cases. So there's the case S equal A, and there's the case A less than S. And they use different hypotheses. It's not the same hypothesis.
Oh, okay. Okay. Oh, I see. Okay.
So So it's A equal S plus a weak PCS hypothesis and A less than S plus a stronger PCS hypothesis.
I see. Okay.
Not the same.
Okay, I'll make the adjustments. And then a few years later, this was improved to S less than or equals to A, which basically removes the hypothesis in the case where A is equal to S by Sheila. So what this means is that we came very close to constructing one such family in ZFC, but until now, it is still open whether we can completely remove this set theoretic hypothesis. Okay? And the construction of focus today will be the latest one. So I'll be showing how we can adapt this construction to construct one completely separable map family of subspaces later. Okay. So before that, I want to just give a quick overview of what the proof of the construction is like, so that we can understand how we can adapt the construction later. Okay. So let's start by introducing what a block splitting family is. One second. So you may have heard of a splitting family. So a block splitting family, instead of splitting sets, it splits interval partitions. Okay. So we say that an infinite set S block splits some interval partition if the set S contains infinitely many intervals, Pn's, and also avoids infinitely many Pn's. Okay?
Interval partition is what I think it is. Partition into intervals.
Yeah. So it's a partition of omega into intervals. Yeah. Okay. And of course, a block splitting family is just a collection of sets in which every interval partition is block split by some member of this family. And it turns out that there's a very nice characterization of the size of the smallest such family. This is exactly the maximum of the bounding number and the splitting number. And one reason why block splitting family is of interest in this construction is because of this quick lemma over here, which says that for any almost disjoint family and any positive set X, we can always find some S alpha, a member of this block splitting family, that splits X into two disjoint positive sets. Okay? Let's take a quick look at why this is true. Let's consider two cases. Well, if there is some subset of X that is almost disjoint from every element of A, so any subset of omega that is almost disjoint from every element of A is instantly IA positive. Okay? So if we have such a Y, then we just need to find some S alpha that splits Y into two infinite sets. And it turns out that block splitting family is also a splitting family. So therefore, we can always guarantee that such an S alpha exists. Otherwise, then by induction, we can pick countably infinitely many AIs which are compatible with X. So we can just define the interval partition so that for every I, almost all Pn's intersect non-trivially with X intersect AI. Okay, and if we choose this particular interval partition, and we let S alpha block split P, then we can check that X intersect S alpha is compatible with every AI, and similarly X minus S alpha is also compatible with every AI, and so they are both IA positive. Okay, very nice. So let's get on with the construction. Let's assume that S is less than or equals to A. Actually, the important inequality that we want is max of B and S is less than or equals to A. But it turns out that B less than A is in ZFC. So they are equivalent. Okay. Some quick notations. I'll be using superscripts to denote either the set itself or its complement. Okay, so let's fix the block splitting family. I'm going to define this tau. So this tau is a binary function on some ordinal alpha. I have not defined what alpha is yet. I'll define it in a moment. And this tau is defined for an arbitrary almost disjoint family, not necessarily maximal, and some IA positive set X. Okay. So this alpha is chosen to be the least ordinal that splits X into two positive sets. We know that this exists because of the previous lemma. So what this means is that for any beta less than alpha, there is one unique component which is positive, right? It's either X intersect S beta or X minus S beta. So this tau is going to record the component which is positive. So if, let's see, so if X intersect S beta is positive, then we just let tau of beta to be equal to 0. If it's the other one, so X minus S beta that is positive, then we just let tau of beta be equals to 1. Okay? One quick observation is that if Y is a subset of X that is also positive, then the tau of Y is going to extend the tau of X. Okay? Okay, induction step. So let's cofinally enumerate subsets of omega. So what I mean by cofinally enumerate means that every infinite subset of omega is enumerated cofinally many times in this enumeration. Okay? So we're going to construct this mat family inductively, but at the same time, we're going to construct this sigma alpha, which is another binary function on ordinal, such that it satisfies these properties. First of all, a sigma alpha should not be an initial segment of an earlier sigma beta. Secondly, X alpha, if X alpha is positive with respect to IA alpha, then we'll choose A alpha in this induction so that A alpha is a subset of X alpha. So of course, this property is precisely to make sure that this construction gives us a completely separable mat family. And just one more condition, but we won't be discussing this condition for this talk. Okay? So like I mentioned, if we can complete this construction, then A is completely separable. Okay, induction step. So let's say we have defined A beta so far for beta less than alpha. So, oh yeah, sure.
And presumably, condition 2 has something to do with the sigmas.
Yes.
We're establishing condition 2 has something to do with the sigmas. Right? Because otherwise, there's no need for the sigmas to be.
Yeah.
It's not clear what they're doing yet.
Yeah. We won't really be seeing what the sigmas are doing this talk, unfortunately, but they are there. Yeah. Okay, so what we're going to do in the induction step is we are going to define a tree of positive sets. Okay? So the base case, the XMT, if X alpha is positive, then we'll start there. We'll start with X alpha. If it's not, then we'll just let XMT be whatever. It doesn't matter. So if XS has been defined, then recall that the tau is a binary function that records the positive components, right? And the domain is precisely the least ordinal that splits it into two positive sets. So which means that if XS has been defined, then we can define the next set, XZ0, to be the component XS intersect S alpha S, while the one side will be XS minus the S alpha set. So once again, because alpha S is chosen to be the least ordinal that splits it into two positive sets, so in this induction, every XS is positive. Okay? So, and it's not too hard to check that this eta, which is the taus, respects taking initial segments. So this is a tree of sets that is defined on finite 2 to the power of less than omega. So what this means is that if we take some f in 2 to the omega, then we can consider the xs, which is the initial segments of f, right, which is xf to the restricted to n. And because of this observation, this is an increasing sequence of binary function. Increasing in the sense of initial segment, of course. So we can take eta f to be the union of these binary functions, and this is a perfectly well-defined function. And the domain of eta f, which is the countable union of the domains of eta fn, is still less than max of BNS because it has uncountable cofinality. Okay? So this is well defined for any function f in 2 to the power of omega. But we're going to fix one f in which eta f is not an initial segment of any of the previous sigma betas. Because if you recall, in the induction step, one of the criteria is that sigma alpha cannot be an initial segment of a previous sigma beta. And of course, this is possible because there are continuum many binary functions of omega, but so far we have only defined less than continuum many sigma betas. Okay? Okay, nice. So basically what we have done is we have defined a tree of sets, of positive sets, and we take this special f, and we consider this branch of sets, right, with respect to this f. This is a branch of decreasing, is a chain of subsets of positive sets. And because I plus A alpha is a selective coideal, which means that there is some y that diagonalizes these xfn's, which in particular means that y is an almost subset of xfn's. And this is a very special y because it turns out that under this y, we can find a subcollection of A alphas of size strictly less than max of B and S, which serves as a litmus test if a set is almost disjoint for every A beta. Of course, this only works for subsets of Y. That's why this Y is so special. So this is the claim where we can see the powers of the sigma alpha. Unfortunately, I'm going to black box it. Okay. Okay, but what this means is that instead of checking every previous A beta, we just need to check this subcollection that we know is of size strictly less than max of B and S. And you probably can see why we want to assume that the max of B and S is less than or equal to A now. We just need to consider the intersection of these sets with Y. And this is an almost disjoint family of subsets of Y, right? There might be some finite sets, but we don't care. Okay? So this is an almost disjoint family that is smaller than the least possible cardinality of the almost disjoint family. So therefore, we can fix some A alpha inside Y that is almost disjoint from every element of C prime, and therefore C. And because this C is a litmus test, this implies that A alpha works. Okay, so this is the overview of the construction of the normal completely separable map family. Are there any questions? Okay, so enough of omega. Let's talk about vector spaces again. So of course, at the start, I defined completely separable map family in terms of IAs and stuff, right? So naturally, I have to do the same for vector spaces. But before that, unfortunately, I have to define even more things. In the case of omega, I have to define, okay, sorry. In the case of omega, there's infinite versus finite. So the natural comparison for vector space is whether it contains an infinite dimensional subspace or a finite, or it doesn't. But it turns out that this is actually not the best comparison, and I'm not a very creative person, so let's just call it big and small, okay? So an arbitrary subset of E is big if, well, it contains some subspace inside it, and if it's not big, then guess what, it's small. But we also need this notion of very small, in which Y is not only small, but it also would not blow up another small set into a big set. Okay, so to be precise, if you take a union with another small set, it stays small. And there's a very good reason why we needed this notion of very small. In the case of omega, finite union of finite sets is finite, right? But finite union of small sets need not be small. So here's an example. In the case where F is, we are dealing with a vector space of, we are dealing with a field of more than 2 elements, there's a very explicit set which is small, but the complement is also small. So let me just quickly explain why this is true. So let's just fix some mu. There is neither 0 or 1. So every vector x can be written as lambda en plus y. So en here is the very first en with non-zero coefficients. And y, the set y, is asking whether this very first coefficient is equals to 1 or not. If it's equals to 1, then we put it in y. Otherwise, you're not inside y. And this can't contain a subspace, right? Because if I take some subspace U and some vector x, we can just divide this x by the very first coefficient, and then now the very first coefficient becomes 1. So this is now inside y. But then, well, we can also multiply it by mu to make the coefficient not 1. And so this vector is now not in y. And again, of course, we are just taking scalar multiplication, so all these vectors are still in U. So what this means is that Y does not contain any subspace. Y complement doesn't contain any subspace, but the union is a whole E, which is big, of course. So this tells us that the definition of big and small, the contrast here, is not perfect. It's not completely analogous to infinite and finite sets for omega. But let's just assume for a moment that everything works very well and just, okay, I'm just going to define IA anyway and hope everything works out. Yep.
This is an example of
a two coloring with no
coloring.
Yeah, a bad two coloring.
Yeah, bad two coloring.
Yes.
Okay. Yeah, good. Right, once the field has more than 2 elements, then you use the digital, and so all the
That's right.
that you know.
Yep.
Gone. Yeah. Okay.
Okay, so like I said, I'm just going to ignore this problem and just define and try to define IA anyway. Previously, for omega, we defined IA to be the set of Y which is almost covered by finitely many subsets. And by almost covered, it means that the remainder is finite, right? So in this case, instead, let's consider we replace finite with small. And because of what I just said just now, this IA is not an ideal, right? Because finite union of small sets can be small. But again, I'm going to ignore this issue and just define I plus A and I plus plus A anyway, which is the exact same definition. I plus A is just the complement, and I plus plus A is a set of subsets of E which are compatible with infinitely many elements in A. Okay, horrible. So IA is not an ideal, but it turns out that it's actually pretty close to being one. It is almost an ideal. I will clarify what this means later, okay? But let's use this issue one as a promise. It's a promise that I'll get back to you guys on what I mean by this, okay? So, but the point is that even though IA is not an ideal, it is ideal-ish enough for us to proceed with what we want to do. Okay, so let's define completely separable map families. Same thing, any positive subspaces contains some subspace inside A. Again, no, it's due to me. Yeah.
You didn't consider this stuff.
No, he didn't. Quick remark is that, I mean, there are a few natural ways to generalize completely separable map families to the case of vector space. For example, you may ask whether if we really need this subspace requirement, and it turns out that the answer is yes, we do need U to be a subspace over here. Okay. So in the case of omega, like I mentioned, it's still open whether there's a ZFC construction of a completely separable map family. And what I'm explaining here today is that in the case of vector space, we can construct one in ZFC. So let's see why this is the case. So basically what I'm going to do is I'll try to repeat the construction that I just mentioned. I'll adapt it into the case of vector space. Okay, because life is not perfect, we have to make changes here and there. And I will accumulate the changes and as an IOU, okay? Okay, I mean, I say it's an IOU, but in the end, I'm going to address less than half the issues anyway, so. Okay.
And the first one is
Yeah, the first one is one of them. Yeah, good news. Okay, so again, let's fix a block splitting family. But block splitting family is a collection of subsets of omega, but we are dealing with vectors, right? So instead, what I'm going to consider is I'll consider the span of EX, where n is in each of these S alpha. And previously, we showed this lemma where block splitting family, there's always some member that splits a positive set into two disjoint positive sets. We have a similar lemma in the case of vector space. So that analog will be number 4.
No, okay.
Okay. Excuse me. So number 4 is the analog where there is some alpha that splits some block subspace B into two positive sets. But so what are these 1, 2, 3 dealing with here? So let's take a look at number 1. Number 1 says that for any alpha, B intersect Z alpha is positive, or B minus Z alpha is positive. Well, in the case of omega, that's like obvious, right? Because it's an ideal. But like I mentioned, in the case of vector spaces, IA is not an ideal. So this is actually not straightforward. It's not immediate. As for 2, so 2 says that if B intersects Z alpha, so this is an intersection of block subspaces, and this is positive. But, well, there's a very good reason why I introduced block subspaces, because it's easier to work with, right? It's not clear whether intersection of block subspaces is a block space. But what this lemma tells us is that, oh, that's fine. It doesn't matter, because if B intersects Z alpha is positive, then actually we can refine this intersection to a block subspace while staying positive. Okay? And number 3 is worse, right? This is not even a subspace, right? This is B minus a subspace minus another subspace. But again, we can refine this set into some block subspace while staying positive. So what this means is that essentially we can use this lemma while kind of assuming everything is a block subspace. It's dense, kind of. Okay, so we have this main lemma. Yes.
Zero is not in that difference.
It is because we are ignoring 0. Yeah. 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 Okay, yeah, so previously we assumed S is lesser than or equals to A. So of course the first step to think is to do the same for A vec. That's the cardinality for map families of box subspaces, right? But actually we don't have to do that because we already know that this is true in ZFC. It turns out that A vec is at least the cardinal non-M, which we know is greater than both B and S. So this lemma tells us that, okay, we can start this construction without any assumptions, assuming that the rest of the things go well, of course. Okay, so fix this Z alpha, which is the span of the S alphas. We're going to define this tau again in basically the exact same way. If A is an almost disjoint family and B is a positive block subspace, then this tau is going to record all the positive components. Okay, once again, alpha is the least ordinal such that it splits B into 2 positive components, and any previous beta is going to record the positive component. And once again, if C is a block subspace of B, then tau C extends tau B. Okay, so now we're going to enumerate subspaces instead of subsets. I should have included cofinally. Again, every U alpha is enumerated cofinally. We'll define these A alphas along with the sigma alphas such that the same conditions holds. Sigma alpha can't be an initial segment of a previous sigma beta. If U alpha is positive, then A alpha is contained in U alpha. And the same condition, the third condition, which we will not discuss today. And again, because of the second condition, this will give us a completely separable map family of subspaces. Okay, so again, in the induction step, this time we'll be defining a tree of block subspaces. Previously, we let the base case be the X alpha, right? If X alpha is positive, then we just let X empty be equals to X alpha. This time is slightly different because U is an arbitrary subspace, positive subspace. It need not be block. So, and we need C empty to be a block subspace, right? But it turns out that actually that's fine. If U alpha is a positive subspace, then we can refine it to a positive block subspace. Very good. And then once again, we define eta S to be the recording binary function, the taus, and alpha S is the domain. And we'll define CS0 and CS1 to be the block subspace, the 2 positive block subspace in the respective components. Okay, and so over here, I'm actually using the 2, 3, and 4 of the previous lemma, right? So 4 splits these 2 into positive components. 2 and 3 ensures that there's a block subspace here and there's a block subspace here that are positive. Okay?
About something. Would it be enough to just enumerate the block subspaces to get your completely separable Met family? By enumerating all infinite dimensional subspaces. Could you just enumerate the block ones?
Oh, but in that case, so we define completely separable for arbitrary positive subspace to contain a subspace in A, right? So does this U contain a positive block subspace? Yeah, so A posteriori, there's no difference, but A priori is not clear. Water? Okay, so once again, we can consider eta f. We take the union of eta fn's. And so this eta f gives us a function with domain less than max of b and s. We choose f such that it's not an initial segment of any of the previous sigma betas because that's what we need in our induction hypothesis. And we let this eta f be our sigma alpha. So the next step that we did was to show that there's a diagonalization, right? Because, so in this case, the CFN is going to be a decreasing sequence of block subspaces, a chain of block subspaces. So we know that I plus A is a selective coideal in the case of omega, and it turns out that there is also a corresponding notion of selectivity for I plus A for subspaces as well. So therefore, we can indeed take this D as a diagonalization of this chain of positive sets. Very good. And this D will correspond to the previous Y, which is the magical Y, right? Because we can get a limit test of this C of size less than max of B and S, and we just need to test whether a subspace of D is almost disjoint from every element of B. That's enough to conclude that it's almost disjoint from every A betas. Okay, so then I'm going to take the intersection, and this is another issue, right? Because like I said just now, this is the intersection of block subspace, and it's not clear if intersection of block subspaces is a block subspace. But good news that it turns out that it is. Okay, so this is not immediate, by the way. So what this means is that C prime is an almost disjoint family of block subspaces of the block subspace D. And so we can apply the same argument. C prime is an almost disjoint family of block subspace that is lesser than the smallest possible cardinality of an almost disjoint mad family of block subspace. So therefore, we can get some block subspace A alpha that is almost disjoint from every element of C. If we did not know that finite intersection of block subspace is a block subspace, then we can't apply this inequality here. It's possible to define a similar cardinal invariant for the case of our mad family of subspaces, not necessarily block. It's not known if this is greater than max of B and S. I know that you are convinced that it is, but well, there's no proof in literature at the moment. Yeah. Yeah.
We'll talk about it.
Sure.
And did you have a proof before with this other variant?
Yeah. So in the older version of my paper, I didn't have this lemma, so I have to assume this inequality. But because I have this lemma, I can just remove it. Okay. So I promised. I don't use the word promise because I didn't really promise anything. So okay, these are the issues that we talk about in the proof, which is first thing is that I say that IA is almost an ideal. Well, yeah, whatever that means. Then we have this corresponding lemma for Z alpha, not S alphas. Then we have this issue where we can refine an arbitrary positive subspace into a block subspace. And then we have this issue about selectivity, right? So, but, well, I can only fulfill about half of this IOU. Actually, it's less than that. But so I'll be focusing the rest of the talk on showing these two things. Okay? So let's take a look at the first one. So before I explain what I mean by almost an ideal, I need to show some relationship between small and very small sets. So the example that I gave earlier, what I showed is that there is a small set that is not very small. Well, what I'm saying here is that when we are dealing with subspaces, then small subsets are indeed very small. So let me just say this. So I'm including these two cases because it's sufficient for most of the work. Excuse me. But I believe that it goes far beyond. So personally, I think that if we take Boolean combination, we can still make sure that small sets are very small. That's what I think. But let's just prove this for these two cases. Sorry, let me go back to this. The first statement is essentially saying that finite dimensional spaces are very small. And the second case is, well, U minus V is small, then it's very small.
Or infinite dimensional subsets.
Yep. An important consequence of this lemma is that it's not possible for a subspace, infinite dimensional, of course, by default. It's not possible for a subspace to split another subspace into two small components. This is an important consequence. So let's take a look at the first proof. Okay, we need to show that it's very small, right? So we just fix some subset Y and suppose that it contains some subspace W in this union. We need to find a subspace that is contained in Y to show that Y is big. But that's not too difficult because U-intercept V is finite dimensional. So I just need to take a finite codimension subspace of W to avoid this intersection. Then W prime is an infinite dimensional subspace that is inside Y. Okay. For the other case, if W is inside U minus V union Y, we need to find a W prime in Y. Let's consider these three different cases. If W intersect U is small, then we just need to take a subspace that avoids this intersection. And it avoids U, which implies that it avoids U minus V. So W prime is going to be inside Y. If U intercept V is big, then that's very good, right? Because U intercept V already avoids U minus V. So this subspace is already inside Y. The last possible case is not possible because if W intercept U is big, but W intercept V is small, then we just need to take a subspace that avoids V, but is still inside U. But we assumed that U minus V is small. So this is not possible. Okay, so as I promised, when I say that IA is almost an ideal, it means that it satisfies the following. So first of all, it doesn't contain everything. It doesn't contain E. Secondly, it's downward closed. I mean, that's of course, right? Because small sets are downward closed. So IA is not quite closed under finite union, but what this tells us is that it's closed under finite union of subspaces. And again, we can actually say a lot more than that, than just taking union of subspaces, but I'm just including one of the examples to highlight that IA is really very close to an ideal as far as subspaces are concerned. Okay, so let's take a look at why this is the case. If E can be almost covered by finitely many elements of A, let's say V0 to Vn minus 1, then I'm going to take another V, let's call it Vn, that avoids, that is different from all these Vi's, okay? So Vn, so all these sets are small, right? Because it's an almost disjoint family, which implies that it is very small. So Vn is a union of a small set, so this is small because this is small, and finitely many very small sets, which implies that Vn is small. A contradiction, of course. So therefore, E is not inside I of A. Okay, so we need to show that finite union of small subspaces are small. No. Finite union of subspaces in the ideal are in the ideal. Okay. So if U and W are in the ideal, then we can take some, again, VIs, which almost covers U and W. So I'm claiming that this set of V also works for U union W. Because otherwise, if there is a W prime that is inside this subspace, then U is going to split W prime into two small components. But like I mentioned before, subspaces cannot split subspaces into two disjoint small components. And this argument works for a lot of other combinations that you want to think about. So for example, I believe that if V is inside I of A and U minus V is inside I of A, then U should be inside I of A as well. For more or less the same reason, I believe. Okay, so I have repaid one issue. Let's talk about the second issue. So this is the main lemma that I was talking about, where we let Z alpha be the span of S alphas, and we have this bunch of statements over here. I guess it's a bit hard to see on the screen here, but so I'm highlighting 1 and 4 in red because I'm only going to repay these two statements, okay? Please don't charge me interest. So the first statement is, the proof of the first statement is very similar to what I showed just now. That IA is almost an ideal. Okay? So again, suppose for a contradiction that there are some VIs in which both B intersect Z alpha and B minus Z alpha are small. But we know that B is IA positive, which means that these VIs cannot cover B up to a small component. So what it means is that Z alpha is going to split this U. So this U is a subspace in this difference. This Z alpha is going to split U into two small components again, which is a contradiction. Okay. And I believe that I should prove this lemma because I proved it for the case of omega, so I should at least show what it's like for the case of vector spaces. Okay, so in the case of omega, I split it into two cases, and I'm going to do the same here. Let's first suppose that there is some block subspace C that is almost disjoint from every element of A. So previously, we just need to split the Y into two infinite sets. And here, we have to do something similar, but we do need the interval partition to help us out. So what I'm going to do is that I'll define this interval partition such that this Pn contains the entire support of Xn. So what this means? So I guess I didn't write that S alpha should split the interval partition. Because S alpha contains infinitely many Pn's, it contains the support of infinitely many Xn's, which implies that infinitely many Xn will be inside this Z alpha. Okay, so because there are infinitely many vectors in C, there should be an angle bracket here and here. Because there are infinitely many vectors in C, there are also in Z alpha. Therefore, I guess infinitely many linearly independent vectors. So therefore, C intersect Z alpha is an infinite dimensional subspace that is almost disjoint from every element of A and is therefore IA positive.
Applying max BNS, we don't actually need an interval partition. Works for just any partition into finite sets.
Ah, I see. Okay.
You don't need them to be convex, which means here you're saying you want to take your Pn to contain support Xn. your supports need not be convex, right? I mean,
Yeah. Yeah, it need not be convex.
then you might have a problem getting an interval partition with that problem.
No, because these are block sequences. So
Oh, I see. So the Cn. Oh, so Cn is a block sequence.
yeah, so Xn is a block sequence. That's right. Yeah.
But still, I mean, you don't need that at all. I mean, it's max BS just works for any partition in finite sets.
Okay. Okay, I see.
I guess vector spaces with a block set is the same as vector spaces simply generated by vectors whose supports are disjoint, not necessarily blocks. I mean, you just permute the Hamel basis and you get.
Oh, I see. Yeah. Yes. Oh, yeah. Okay. Yeah. Okay. So let's continue. And similarly, there are infinitely many. So S alpha avoids infinitely many supports. So one quick observation is that one quick observation is that the span of En not in S alpha is in the complement of Z alpha. Okay, and all these Xn's in which the support is avoided by S alpha will be inside the complement. And so therefore, C minus Z alpha contains sorry, not quite contain this subspace, but it contains an infinite dimensional subspace of this subspace. So therefore, C minus Z alpha is big and is almost disjoint from every element of A alpha, of A, sorry. Okay. So what was the other case? So similarly, if there is no such C, then we can pick infinitely many VIs which are compatible with P. Okay. So let's fix an infinite to one surjection. And I'll define this block sequence this way. So I'll just choose x0 to be some vector in B that's also in V of gamma 0. Okay. And then I'll choose xn the same way, xn plus 1 the same way, but I just need to make sure that this is a block sequence. So in this construction, infinitely many vectors from Vi are chosen because this is an infinite to one surjection. So in particular, this C block sequence is compatible with every Vi. So let's define an interval partition like this. Yeah, I guess in this case, I don't need interval as well. Finite sets work, but let's just define an interval because that's what I did. I just let P0 to be big enough to contain the support of X and naught, which is a vector I chose to be in V0. And again, if Pm is defined, then I just let Pm plus 1 be an interval long enough to contain at least one support of a vector in Xi, Xn, where gamma n is equals to I for some I lesser than equal to n plus 1. So again, what I'm doing here is actually pretty similar to the case of omega. I'm just choosing an interval partition so that almost all intervals contain, no, let me rephrase that. For any I, almost all interval contains an element in the intersection of B intersect Vi. Okay, that's the key property of this construction. And so if S alpha block splits P, not just split, then we can, like I mentioned, there will be infinitely many S alpha is going to contain infinitely many. S alpha is going to contain the support of infinitely many vectors of Vi for each I. And similarly, it's going to avoid the support of infinitely many vectors from Vi for each I. Okay? And so from a very similar argument to what I mentioned for the case of for the first case, we can conclude that both B intersect Z alpha and B minus Z alpha are big, and they are compatible with every single Vi. So what this means is that they are in I plus plus A, therefore in I plus A. So there are a few small subtleties here. For example, the containment I plus plus A in I plus A in the case of vector space is slightly more, just a little bit more difficult to prove than the omega case. And there are some other things that I omit. But this is the idea of the proof. I swear when I went for a dry run, yeah, I actually went over the clock, so I'm not sure why there's so much time left. But okay, but thank you for listening.